Hello everyone. In this video, we are going to learn about the experiment to determine the field along the axis of a circular coil. Before going to the experiment, we will recall some of the basics of the magnetic field. In a bar magnet, the magnetic field lines look like this. Outside the magnet, it points from north to south, and inside the magnet, it points from south to north. Consider a wire, and we are placing a compass box near to it. It will not show any diffraction. Suppose if you are connecting to an external battery and the current is flowing through it, the compass shows a diffraction. This shows that a current carrying conductor produces a magnetic field. Now, consider a wire carrying a current I, and this is an elemental length vector dl. Suppose we want to find the magnetic field at a point P, which is at a distance r from the elemental length dl. How can we find this? For this, we have Biot-Savart law. The law states that the magnetic field is given by this expression. Using the Biot-Savart law, we can find the magnetic field of a current carrying loop at a distance x from the center, and it is given by this formula. The plot of the magnetic field versus x is shown here, and the magnetic field will be maximum at the center. To obtain this, we have to put x equal to 0 in the expression. Consider a bar magnet, and for a bar magnet, there is an important quantity called magnetic dipole moment, and it is generally denoted by the letter m, and it is a vector quantity. If you are placing the bar magnet in an external magnetic field, it will experience a torque and it has a potential energy. And the bar magnet will always try to align along the direction of the external magnetic field. Suppose there are more than one magnetic field, then the bar magnet will align along the net magnetic field. Earth possesses its own magnetic field, and the Earth's magnetic north is near to the geographical south. If we suspended a magnetic needle, it will align along the Earth's magnetic field. Consider a circular coil, and this is the plane of the coil. If we align the plane of the coil parallel to the Earth's magnetic field, and if you pass a current through the coil, there will be an additional magnetic field along the axis of the coil. Now, if you place a magnetic needle along the axis of the coil, it will point around the net magnetic field direction, and this is called the tangent law. The aim of the experiment is to determine the magnetic field along the axis of a circular coil, and the apparatus required are magnetic compass, bar magnet, power supply, ammeter, 4-way plug key, rheostat, connecting wires, and the circular coil apparatus. This is the schematic diagram representing the connection between different components. This is the picture of the arrangement of the experiment in the laboratory. Before setting up the connection, we have to arrange the circular coil apparatus in such a way that the plane of the coil is parallel to the Earth's magnetic field. Now, we will place the compass box at the center of the coil. And then, we will rotate the whole apparatus until the aluminum pointer reads 0, 0. After arranging the circular coil apparatus, we will set the number of turns by choosing the appropriate terminals, and it is connected to one pair of the 4-way key. And from the other pair, one is connected to rheostat, and from the other, it is connected to ammeter, and from ammeter, it is connected to power supply, and from there, back to rheostat. Now, we switch on the power supply, and we'll make sure that there is a flow of current. After that, we will adjust the rheostat and make the deflection of the aluminum pointer between 30 and 60, and we will note down the current. Now, we will displace the compass box from the center of the coil. And then, we will measure the distance as x. And note down the deflection as theta 1 and theta 2. Now, we will introduce a bar magnet and adjust its position so that we get 0 deflection. And measure the distance between x and center of the bar magnet as d1. After removing the bar magnet, we will reverse the current direction using the 4-way key. And again note down the deflection as theta 3 and theta 4. This time, we will reverse the polarity of the bar magnet and again adjust its position so that it creates 0 deflection. And like before, we will measure the distance between x and the center of the bar magnet as d2. We will repeat the same procedure in the opposite side also. And from here, we will get the deflection from theta 5 to theta 8 and d3 and d4. And we will repeat the same procedure for different x values. This is the observation table for the different compass box deflection for different x values. Using this, we can find out BC and B. This is the table for the distance of the magnet for different x values. From here, we will calculate M. Here are some of the precautionary measures that has to be followed during the experiment. Remove the magnetic materials, if any, from the vicinity of the apparatus. Avoid parallax error during the measurements. Current should remain constant throughout the experiment. Don't tilt the compass box out of the plane. Thank you.